So, yeah, I just wanted to give kind of a brief review today and then talk about a handful of things. Yes, I believe it says recording. Now, we didn't hear the voice, but it says recording on the screen though. So, but yes, so just want to give a brief review and then talk about the couple of things that I wanted to conclude with. So just a review of, of what we've done and where we're headed. Last time it was like that, but it was actually, it was recorded. So I have faith in the technology, but I appreciate the concern. Yes. So, so we're interested in differential equations like of this form. Where X is highly irregular, namely not differentiable. Okay. And of course, we translate this to the integral equation. Translate this to the integral equation, and we need to define this because if X is not a bounded variation, standard techniques don't apply. So need to define integrals of this form where F is smooth and X is in C alpha for some alpha, okay? Now, as we talked about before, if X is a semi-martingale, we have the Ito theory, so I'm not gonna write that down. The important thing is if alpha is between 1/2 and 1, we have that Young theory, which just says that we can define this as a Riemann-Stieltjes integral. And then the case that we're interested in would be if alpha is in 1/n+1 to 1/n. And then say n is greater than 1, right? Okay. So in the Young theory, we can just do a Riemann-Stieltjes integral. Then for the this other case, we have to add these correction terms. So in before I gave this computation of how like the first iterated, or I guess would be the second term, the second iterated integral shows up. Let me just do the same computation for 1/n+1 to 1/n. I've been sticking to the 1/3 to 1/2 just out of convenience, but we can have this for any n. So we want to define this. So what we do is we take a partition of 0 to t. So take partition, maybe a sequence of partitions with the mesh size going to 0 of 0 is equal to t 0 tn, which is equal to t. And we want that integral to satisfy that it's linear, and Chassel's relations, which is just the integral from a to b plus the integral from b to c is the integral from a to c. So what we can do is we can write this integral over k equals 0 to n. minus 1 of tk to tk plus 1. Okay. So right now, this isn't defined. I'm just saying if it satisfies these things, these are computations we can do. Okay. Then we can Taylor expand F. We're assuming F is as smooth as we want. We can Taylor expand it. And before I Taylor expanded one time, but we could Taylor expand as many times as we need. So then this becomes sum from k equals 0 to n minus 1 of tk to tk plus 1 of f of x of tk. Let me actually erase all of this. Plus f prime of x of tk, x of s minus x of tk, plus blah, blah, blah. Let me write the second one just to be very, very explicit here. X of tk, x of s minus x of tk squared, plus blah, blah, blah. Plus we can Taylor expand it up to order s minus tk to the power of, so this would be to the power of n alpha. So you can Taylor expand up to whatever order you want. That depends on the regularity of x. So the n there is how whole their continuous x is. And then this guy right here, well, if we chose it so that way n alpha was greater than 1. Right? Okay. So we can distribute this and use linearity, and we end up with 0 to n minus 1 of f of x of tk. And then we have the integral dxs. So I'm just going to write that as x, as say like x1 tk plus 1, as just because this is independent of the s, so we can pull this out of the integral. And then just the first iterated integral from tk to tk plus 1 dxs is x1. Then we have plus f prime of x of tk. Then we have x of s minus x of tk integrated against xs. So this guy, we could just, this is an x1, not an x prime. Exactly. So here I'm using as a prime, here I'm using as a 1. So it helps. x1, and then that's f prime. Yeah. So then you have the first iterated integral, which is this guy, and you integrate it against dxs again. So you end up with this x2 tk plus 1. And then here, this squared term, which would be basically the result that you get from integrating twice, then you integrate against x, then that becomes an x3. And then the 2 here is also a part of that. So you get f double prime of x of tk. Then you get x3 tk plus 1 plus blah, 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 plus an order of tk plus 1 minus tk, the n alpha, where n alpha is greater than 1. So we have this entire sum here. And the hope is, as the partition size, as the mesh size goes to 0, the remainder will go to 0 because n alpha is greater than 1. And then all the rest, you have these iterated integrals. And if you're able to define these iterated integrals, then the hope is that this thing converges. It does, which is the sewing lemma. But the, is that supposed to be n plus 1? It should be n plus 1. Yeah. Yeah, you're right. Sorry. It should be n plus 1. Yeah. Should be n plus 1 alpha.
So, I mean, if the stop, the verb before.
Oh, yeah. Sorry. That, and then, yeah, then this is n alpha, and then here is n plus 1 alpha. You're right. Sorry. Plus 1 alpha. So here it's not that, but here we have n plus 1 alpha is greater than 1. So here it's n alpha, but then when we integrate it, we pick up another tk plus 1 minus tk to the power of alpha. So then here we get n plus 1 alpha. Yeah, thank you. Yeah, that's right. That's right. So the point is, if you can define all of these iterated integrals, you have this remainder term that is, that'll go to 0. And the sewing lemma, which I'll prove soon, is actually saying that this happens. All right. Yep, that's right. And the x2, so the point is, yeah, once you have the x1, the x2, then you just compute all of them. And then at some point when the n plus 1 alpha is greater than 1, then you're just integrating, and then you can have in the Stokes sense. And there's nothing, there's no problem there. Yeah. So now so this right here is what is called a rough integral if all of this exists. So let me just define one thing about the rough integral before we go on to the main thing that I wanted to prove today. Mm-hmm. The x1 is just the difference of the path. X2, it's a matrix of the iterated integral. Yeah. Mm-hmm.
We have to assume like this. We just say the tensor of two different.
Well, it's not necessarily going to be the tensor of like two differences. It's just going to be something, and it's just going to be a matrix that satisfies these Chen's relation that satisfies this 2 alpha holder. But yeah, the point is, and I'm going to prove today that you can actually construct a rough path above a signal. That's the main thing I wanted to prove today. For any signal, yeah, for any signal. For me, I'm just going to stick to the 1/3, 1/2, just because it's easiest to construct this. And you know, when alpha gets smaller, it actually does become harder to construct, and there are some like barriers to constructing these. So even as I said with FBM for h less than 1/4, constructing a rough path above FBM with h less than 1/4 is really hard to do. There's been some work done on it, but the work that's been done on it, the rough path on like S to T involves points outside of S to T. And you can't construct one with just points inside S to T. I think there's some like no-go theorems for that. So it's kind of it's a weird rough path that exists and formally satisfies things, but it wouldn't satisfy some relations that we would really want or expect it to. Okay. So before I get into that, let me just remind you, let me just say like the ultimate goal here is going to be defining a rough integral. And I'm not gonna get too too into it, but I just want to define the class of integrands we're looking at. Okay. So definition. Given X in C alpha, so just alpha whole layer signal, alpha between 1/3, 1/2. Okay. We say Y in C alpha is controlled by X if there exists Y prime also in C alpha, so that Y of T minus Y of S is equal to Y prime of S, X of T minus X of S, plus a remainder term of ST. Let's just say, I'll just leave it there, with the remainder term being 2 alpha. Okay, so, I mean, here is a very slight generalization of the idea of a, if F was a function, that Y prime here is just F prime of X of S, right? However, here we're just saying we're allowing Y prime to be, Y and Y prime to be anything that satisfies this Taylor type expansion. And it's a slight generalization from F of X of S, but an important one. And let me just say, we can define the rough integral as the limit as the mesh size of the partition goes to 0, k equals 0 to n minus 1, say, y of tk, x1, pk, tk plus 1, plus y prime of tk, x prime, or x2 of tk, pk plus 1. And for higher ordered ones, you just have a higher Taylor expansion here. All right. So if that thing exists, so if this limit exists, if the limit this exists, it is called the rough integral. Of Y against X, denoted by where I just use this notation, this bold X is X1, X2, the pair. Okay. So we'll talk about controlled rough paths later on, but I just wanted to say, yeah, it's just times, yep. That was just a mark from before, but yeah. So the point is that the computation that I had done, or the heuristic that I had done where you Taylor expand, anything that satisfies some kind of Taylor expansion like this is going to be, is something that we can integrate. So we can generalize it slightly in this way. One other thing is, in general, the Y prime might not be unique, generally speaking. We're just saying there exists a Y prime. However, in practice, this doesn't really matter. So for example, one thing that's a consequence of a result that I have is that for any Gaussian process, say the Holder continuity greater than 1/4, the rough integral does not depend on the Y prime. That's just a consequence of a result that I have. The way it's written, it does depend on the y prime. So if y, y might, yeah, it might actually depend on the y prime, and the y prime might show up in the expression that you have. But in most cases, it just doesn't. Okay. Uh-huh. It doesn't, there's no RST in the limit. Yep. We're just saying that the remainder is of 2 alpha. Yep. Yep. So yeah, the RST doesn't even show up in there. It's just saying we have a certain remainder. Yeah. Mhm.
So in this definition, as the remedy theory is supposed why controlled by X, but now what is equal Y?
Yeah. We're assuming. So I'm saying if Y is controlled by X, then this is the rough path or the rough integral. Yeah. So if the limit exists, so if Y is controlled by X and this limit exists, well, I mean, in general, if that limit exists, then it is the rough integral. We say that's the rough integral, but we can show that it exists if Y is controlled by X, right? So, yeah. Any partition where the mesh sizes goes to 0. Yeah. We'll get into, it'll be the sewing lemma, and we'll get into that soon. So, so that's the rough integral. I just wanted to mention the couple of things that I wanted to hit in the remainder of these lectures. There's 3 main things that I want to talk about. One of them I'm going to present today. So I mentioned the rough integral. Actually, before I do that, just one really big point. So this y here is what is called a controlled rough path. A couple of things to note: it is not a rough path, first of all, because the second order term is just C alpha. So that's one thing important. Second of all, it's not controlled in the sense of like it's a rough path with some control function from control theory. So that's just like one thing I wanted to mention. A controlled rough path is just the kinds of integrands that we can handle. Okay. So let me just say the handful of theorems that I want to, it's 3 theorems that I want to talk about. So for the rest of lectures is going to be, the first one is going to be existence of rough path above some X, and that is the Lyon's Victor extension theorem. From 2006. So first, in order for any of this to make sense, we have to know that we can construct a rough path above a signal. Okay. The second thing is we need to show that the rough integral exists. So show rough integral exists. And that is the sewing lemma. Okay, so I want to prove the sewing lemma that shows that this exists. And the final thing that I want to show, just from the perspective of rough paths, is going to be existence uniqueness of solutions to rough differential equations. Uniqueness of RDE, rough differential equation solutions. And so this is the remainder of like the theory of rough paths. And then one thing that I would like to present on would be an application of this to pathwise stochastic control. So apply to stochastic control. In particular, there was a paper by it was Deal, Fritz, and Gassat, where they were able to do some things with pathwise stochastic control I was planning on presenting. And so the first thing that I wanted to talk about was the existence of a rough path, and that's Lyons-Victor extension theorem. All right. And for this, I must warn you guys, the construction they give might be a little bit unsatisfying in some ways, because it's not how you would construct a lot of these things in practice, but it does demonstrate the existence over any signal. It's a little rough. That's right. So yeah, I'm gonna give a proof of the Lyons-Victor extension theorem. And the idea of the Lyons-Victor extension theorem is that, and you'll see this a bunch, is that we can define the rough path on dyadic times, and then we can use a lemma and some chaining arguments to construct it for all times. The chaining argument is long and not super enlightening, so I'm just going to state that as a lemma. But then I'll show how you can construct it for dyadic times. Mm-hmm. Mm-hmm. Well, the integral of x dx is not going to admit a Riemann-Stieltjes integral, right? So that's the problem, is that if it doesn't fit in the Young theory, right? So we have to construct it So Lyons-Victor. So let me start off with just a lemma that has nothing to do with rough paths theory, but it's just an important lemma. So let y be a function from the union of n greater than or equal to 0, k equals to 0 to 2 to the n of k over 2 to the n to some metric space E. Okay. And then suppose for all n in n, including 0, and for all k in 2 to the n, the distance of y of k over 2 to the n, comma, y of k over 2 to the n plus 1. It's bounded by 2 to the minus n alpha. Then this implies there exists a unique alpha holder y from 0, 1 to E. Sorry. Yeah, it should be. Yes, sorry, it should be k plus 1. Yeah, sorry about that. Yep. Sorry, it's K plus 1. Yeah. All right. So the point is we can define a lift on just dyadic times, and we can do this inductively. And then this lemma here will give us a lift for all time. Okay. And this lemma here has nothing to do with rough paths. Right? It's just a statement about functions. Okay. So what we want to do is absolutely. Exactly. That's exactly. This is very, very much going to be like Komarov continuity theorems and stuff like that. Oh, using dyadics and everything. It's just a modification of the same theme there. Yeah. All right. So let's construct this inductively. Okay. So let's use induction. Let's start off with n equals 0. So for n equals 0, all we need to do is we need to construct xt of 0, 1, or x2 of 0, 1. We need to construct that so that way for all u in 0, 1, x2 0, 1 minus x2 0, u minus x2 u, 1 is equal to x1 0, u o times x1 u, 1. Okay.
I'm gonna go down to
Yes.
how we're going to, which thing we're gonna do now.
We're proving of a rough path on the dyadics. So we're proving it on just dyadics right now. So starting off with n equals 0, do you guys see a very easy definition we can make for x0, 1, 2? We can just choose. Yeah, x is just in C alpha. Alpha is in 1/3 to 1/2. So we're trying to construct x2 above it that satisfies Chen's relation. Yes. So I'm saying we need to find a definition of x0, 1, 2, the second order one in there. And one perfectly acceptable definition that satisfies this, just define it to be 0, right? So just 0 minus 0 minus 0. And then if u is 1, that's 0 equals 0. All right. So we constructed it for n equals 0. Now we can inductively do it and construct it for, assume that it's been constructed for n. So if we can assume so we want to assume that it's been constructed for n. For n. Okay. And then, so that means that x2, k over 2 to the n, k plus 1 over 2 to the n. Sure.
In this case, we'll have to for x of I comma j, where I and j are 0, 1. That's satisfied for all three, whenever we take it. So we'll say that x 0, 0 is
0.
So then the left-hand side is 0. When you make this convention x0, 1, X2, 0, 1, and 0. The left-hand side is 0 no matter what.
Uh-huh.
The right-hand side, one of those is always 0 because you use either 0 or 1.
Yes.
That's the work.
Yep. Exactly. Sorry. So yeah, that was the point, is that we can, yeah, we just make this convention that this is 0, and remember x1 0 comma u is just x of u minus x of 0, x1 0 or u comma 1 is x of 1 minus x of u. Now, if u is either 0 or 1, if it's 0, this is 0. If it's 1, this is 0. So then if we just define everything to the left to be 0 and then make the right side, we know that the right side is going to be 0 as well.
We should think double the number of points at every point. That's why the previous, we could just say, let's now split it 0, 1 half, 1, try something for that. Let's say you can't do that. You have to double the number of points. So 0 to 4, 1 half. Just keep adding more and more, double the number of points at every stage.
Exactly. Yes.
The next stage is 0.
Yeah, it is 0. It's, we're doubling the number of like intervals, right?
Okay, sorry. Okay.
Yep, we're doubling the number of intervals. Also, one other thing that is implicit in here that I didn't check is that 0, the constant function 0 is 2 alpha holder. So it satisfies all those definitions for, you know, the 2 alpha holder and the chance relation. Yeah, so this is just n equals to 0. Oh, I am excluding the 1/2 for a very stupid reason. Yeah, so I am excluding the 1/2 here, but if you have something that is 1/2 holder, you can make it 1/2 minus epsilon holder for any epsilon, and then you can construct a Riemann-Stieltjes integral, or you can construct this, sorry, not that, you can construct a x2 above that in the space of C alpha minus 1/2 minus, right? So there's just a kind of a dumb thing that happens at 1 over n is that you can show that the iterated integral must be the Riemann-Stieltjes integral. You can show that, which might not exist if we're right on that border, but you can always construct it as a rough path of like in the space C alpha or C 1/2 minus epsilon for any epsilon. So if we're in 1/2, we'll always lose a little bit epsilon, and you'll see you'll see something like that. You'll see like a 2 alpha somewhere, and you know, yeah, you'll see that 2 alpha somewhere. But yes, I am excluding that 1/2 for kind of a silly reason. Right. So inductively, we can assume that we've constructed for n x2 k k over 2 to the n, k plus 1 over 2 to the n. And now we double the number of intervals, and we want to construct it for a double number of the intervals. Okay. So what we can do, we can make a choice. Choose to set x2 to k over 2 to the n plus 1, comma 2k plus 1 over 2 to the n plus 1 is equal to x2 2k plus 1 plus 1, 2k plus 2 over 2 to the n plus 1. So basically, when we double the number of intervals, we're just making the artificial choice, we're just making a choice that on to the left and to the right, that they're equal. We're just making this choice. Okay. And this is totally, there's nothing deep about this. We're just making that choice. It's ad hoc. It's just to show the existence. And in general, you're not going to expect something like this. Okay. And then when we make this choice, we can apply Chen's relation to get a definition for these. All right. So we can recall Chen's relation as x2, 2k over 2 to the n plus 1, comma 2k plus 2 over 2 to the n plus 1. And remember, this is just equal to x2 over k to the 2 to the n, k plus 1, or 2 to the n. But I'm just rewriting it in terms of the dyadics here. And then we can apply Chen's relation to make a choice. Okay. So the Chen's relation here is going to be x2, 2k over 2 to the n plus 1, 2k plus 1 over 2 to the n plus 1, plus x2 of 2k plus 1 over 2 to the n plus 1, comma 2k plus 2 over 2 to the n plus 1, plus then we have the first order term. So I'm just applying Chen's relation here. Plus x1, 2k over the n plus 1, comma 2k plus 1 to the n plus 1 tensor n plus 1, comma 2k plus 2 over 2 to the n plus 1. Okay. So this is what Chen's relation says. So we have that this guy here, inductively, we have a definition for that that satisfies what we want. This right here, we're good with because that's just the first order term. And then we set these two guys to be equal to each other. And that's just a choice that we're making to make this work. Is it? Exactly. So you can solve for the equation. So once you have that, then you just bring everything over. So you have just 2 times this guy is equal to this guy minus that tensor product over there. And then we can make a definition of that.
What about to the point? Arbitrary between A over 2 to the A plus 1 to the combination. Instead of doing half.
Okay, you can do that as well, sure.
We don't need it.
Well, or you mean
You're just weighted half in front, like that's by making them equal, we're saying we do half.
sure. And I mean, yeah, you're asking about like this choice here.
Right.
Yeah, this.
You go run along 1/3 and say, well, it's linear, we're just saying it's linear in between.
Sure.
Or we can choose any point in between.
Sure. So you could make this choice, or you could make it as, instead of like 1/2, you can make it, them add to whatever. Just
You could even put it in a function. But your corresponding, you take something minus 2 and minus 2 or something. And it's also there to show that
as long as you can solve.
Are scalable. Right off.
Sure. And then the one thing that with the dyadics, though, that is nice here is we're going to get a nice relationship for the Holder norms of this. So the dyadics are nice in that way. But for this equation here, you can choose whatever, you can choose multiple things. This is just one arbitrary choice that doesn't have any significance other than that it makes solving for this easy, right? But there's nothing deep going on, or there's nothing meaningful about this choice here. It's just a choice that works.
Verify that the initial intervals either consecutive intervals.
Well, if you have it on consecutive intervals, then you can just, verify it for all of them. Yeah.
Make sure that helps.
Yeah. So we're just checking here, and it's because it's on the dyadics, right? That makes this work. So, if we're on the whole interval, then it's going to be a little bit trickier because it's not a notion of, consecutive points there. But on the dyadics, you're able to do this kind of chaining argument. So we can just check these, iteratively. Yes. Uh-huh. Yes. This right here? Yes, because this is just a first order process, which is given to us. So this is just the increment of our process. That's the increment of our process. So we're able to, that's always well defined. This is defined inductively. And then we're just choosing the arbitrary choice of making these equal. And then we just solve this for these guys. And then as we solved it, it satisfies Chen's relation by definition. And then we can check that it satisfies the 2 alpha Holder condition, right? So yeah, so we just make the decision, x2, 2k, or 2 to the n plus 1, 2k plus 1 over 2 to the n plus 1. We just define this to be the previous guy, the x2 over k over 2 to the n, k plus 1 over 2 to the n, minus this thing right here, x1. We'll have a 1/2 here. x1 of 2k over 2 to the n plus 1, comma 2k plus 1 to the n plus 1. It's 1, 2k plus 1 over 2 to the n plus 1, 2k plus 2 over 2 to the n plus 1. And we just make this choice. And given how we constructed it, this satisfies Chen's relation. Mm-hmm. X2 here.
We'll never choose. I mean, we're just adding more points.
Yes.
So initially we split the difference between something.
Uh-huh.
And then we just walk it in. So
Uh-huh.
if you did what I said, and we say you started off at 1/3, then that would never change in the rest of the construction. But it would give a different answer than the one you did it this way.
Yes. Yep. So lots of different ways of constructing.
Interested in the boundary of something, there's some kind of boundary operator here when we do this Chen's relation. And those things will get killed off because it's like some kind of constant term which you get subtract off after which gets killed in the differentiation process. I can't make that algebraic. That's what it looks like. And, you get something,
Mm-hmm.
but it depends on a lot of choices.
Yes.
In the end, some equivalence class doesn't, and then we're good.
Yeah. Well, one really important thing is, again, remember the X2 is not at all unique, very far from being unique.
Yeah.
So this is just a construction of one rough path above it. It doesn't have to be, and the rough path that we're constructing actually is in many ways pretty stupid. This is not the way people would actually want to construct a rough path in any kind of practicality. This is just an abstract result that we can just inductively show the existence of it. Well, I mean, it might not have a good approximation theory, right? That's a really important thing is, I'll get to, the geometric rough paths and how we can construct a geometric rough path, because we want an approximation theory. We really, if we have like the point is, if we have a rough differential equation, we want to be able to say, okay, if we approximate the noise in some particular way, then we can approximate the solution in a particular way. If we have something like this, just generally speaking, I mean, I'm not really sure how to do an approximation there. Maybe there is some, but I'm not really sure how to do it. But if we were able to construct a geometric one, which we will do, which I'll mention shortly, but then we're able to actually do approximation theories and have kind of natural looking rough path lifts. This is just an abstract result that one exists in generality. So this satisfies Chen's relation just by construction. And then also you can check using, you can just check that for the 2 alpha holder, that so 2k over 2 to the n plus 1, 2k plus 1 over 2 to the n plus 1, 1/2. And then we have this guy here. That's right, yeah. K over 2 to the n, k plus 1 over 2 to the n plus 1/2 times the Holder norm of x times 2 to the 2n plus 1. Then once we have that, we can define a sequence of constants. And then once we define the sequence of constants, this an here, define an 2 to the 2n alpha max 2 to the n once we have the sequence of constants, we can rewrite this in terms of these constants and get the following an plus 1 is equal to 2 to the 2 alpha minus 1 an plus 1/2 x alpha. Now, a very important point here. You're asking about the alpha equals 1/2. While I was excluding the alpha equals 1/2. Do you see a 2 alpha minus 1 there? There you go. So, and then after this, we can show that the an are bounded from this. It's not too bad to show that the an are bounded, provided the alpha is less than 1/2, right? And then, yeah. We could use the chaining argument, the lemma that I wrote before. So the point is we can inductively define the rough path on the dyadics. We can lift it to the entire interval and then construct a rough path above it for any signal. And one really, yeah, go ahead.
Normally we found that some constant times the size of the
Mm-hmm.
Here you have a sum of two.
Mm-hmm.
This first piece, well, it looks like you're multiplying two, but the n alpha.
By the way, one thing I forgot to write here, this should also have a 2 to the minus 2 plus 1 alpha. Sorry about that.
So how does this give you older? Again, I'm just missing that.
Okay, so we can, or sorry. Or actually, sorry, let me rewrite this real quick. So it should be that sorry about that. Should be minus 2n alpha here. Sorry, yeah, never mind. I had it right before. So we have that, and that should be a 2 alpha minus 1. Sorry, it's right the first time. I saw something wrong with my notes, but yeah, it's right the first time.
The including alpha less than 1/2 implies that the sequence is bounded. And how does that do the folder?
It was just from the exact form of the lemma that I had written. Basically, it just, if you look at the distance between these consecutive, and that's bounded up by some constant times 2 to the minus n alpha, then you're able to construct it.
And if we bounded by this, it could go up by the alpha norm of x divided by 2 in each step, right? Every time you do this. Another constant there, so it goes up and up, right?
You can show that it doesn't. You can show that. Yeah.
So here you have a piece that's bounded by constant minus an alpha plus the capital. So the lemma just has. So you see upper bound the sum one.
Yeah. So you can apply the lemma there. Yeah. Let me just say one more thing about this. I know we have close to time or whatever, but I just want to say one more thing. What this does that is really nice though is, okay, so this the extension theorem gives us it gives a rough path above the signal, but it doesn't necessarily give us a nice rough path or a good one. But we can use this and then show that this gives us a nice rough path if we're willing to lose a tiny bit of regularity. So if we lose a little bit of regularity, we're able to we're able to get a geometric rough path. So one fact that I wanted to mention was that in the paper here, they additionally show that you can do this in a geometric way or a weakly geometric, right? So the full theorem is that X, B, and C alpha for alpha and 1/3 to 1/2. Okay. Then there exists weakly geometric rough path above X, where weakly geometric means that the weakly geometric has the condition on the symmetric part. So it's 1/2 x2 plus x2 transpose was 1/2 x1. This is on ST O times x1 ST. So this is what it means to be weakly geometric. Satisfies this kind of integration by parts or chain rule. And then as a consequence of this, there's a very nice embedding of, if you have the weakly geometric, this compactly embeds into full geometric. For all beta less than alpha. So you can get, so a geometric rough path is one that can be approximated by smooth functions. So we have this embedding, it's even compact, which is really nice. So the point is, if you have a signal that's C alpha holder and you're willing to consider slightly less regularity of beta, where beta is less than alpha, then you're always able to construct a geometric rough path above it. You're always able to construct a rough path that has an approximation scheme to it. So here we don't necessarily have an approximation by smooth functions or anything like that. But if we just lose a little bit, we can approximate in just a slightly weaker topology. So that's really the ones that we care about. Because if we have a good approximation for a good approximation for our signal, then we should be able to have an approximation for the rough path above it. And the one proof that I wanted to give next would be like a Donskir's theorem for rough paths, or for Brownian motion, where if you take a random walk, you do piecewise linear interpolation, then you integrate Riemann-Stieltjes and then take the limit in the rough topology of that. That converges weakly to Brownian motion with Stratonovich integration. So that is really the kind of things we want to do. We want to see piecewise linearizations coming from like a random walk, or just piecewise linearizations period, do a Riemann-Stieltjes integral for that, and then take a limit, or some other kind of approximation procedure. Like Francesco, we were talking about the, you cut off a sum of the Weierstrass at n. That's a good approximation. We want to be able to construct it using something like this. The Lyons Victor shows that you're always able to do that if you just lose a little epsilon. Anyway.